Hi, my name is Vincent, and today I want to take a look at implicit differentiation. So we have the problem for the equation x squared y plus 3xy cubed minus x equals 3, find dy dx by implicit differentiation. So for this problem, we really do need to make use of the chain rule. I believe that using the chain rule really helps illustrate this concept of implicit differentiation. So we start by writing the equation for the problem. So we have x squared y plus 3xy cubed minus x is equal to 3. And now what we need to do, we're looking for dy dx, so we need to take the derivative with respect to x of both sides of this equation. So basically what we're doing is we're taking ddx of both sides of this equation. So now think of this as a distributive law problem, where we could take the derivative with respect to x of each individual piece, x squared y, 3xy cubed, and minus x. So in the next line, we could restate this problem as ddx of x squared y plus ddx of 3xy cubed minus ddx of x equals, and now the derivative with respect to x of 3 equals 0 because the derivative of any constant is equal to 0. This is where that fluency with basic derivatives comes in. So now for the next line, we're going to make use of the product rule for finding derivatives. So notice how we're taking the derivative with respect to x of x squared y. And x squared y, they're attached by multiplication. So what we need to do is we're taking the derivative with respect to x of x squared, and we're multiplying this by y, and then we're going to add the x squared times ddx of y, which we could put in parentheses to indicate we're taking the derivative with respect to x of y, and we're taking the derivative with respect to x of x squared. All we did here was the product rule. We have the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece. So now for the next stage, we're looking at ddx of 3xy cubed. Well, same concept. We're using the product rule once again. We're finding the derivative with respect to x of the first piece, which we could say 3x, and we're multiplying this by the second piece, which is y cubed. And now we're adding 3x, which is the first piece, times the derivative with respect to x of the second piece, which is y cubed. So we have times ddx of y cubed minus the derivative with respect to x of x. Well, using our fluency with basic derivatives, we know that the derivative of x is just 1. Or if you think of it as dx over dx even, that also equals 1. So we have minus 1 equals 0. So now what we need to do, this is where the chain rule is going to come in. For any of these pieces where we're taking the derivative with respect to x of some other variable, in this case y, we're going to use the chain rule. But for now, let's just take care of the simple pieces. ddx of x squared is equal to 2x. All we're doing is using that power rule for finding the derivative of some exponent term. So we have 2x times y now. Because notice how ddx of x squared, this whole expression simplifies to 2x here. And then we're just multiplying that by y. So now we have plus x squared times, and now you may know that this looks like dy dx already, but let's say we want to use this chain rule. We can't take the derivative with respect to x of y, so what we're going to do is we're going to take the derivative with respect to y of y, and then multiply by dy dx. And now what this accomplishes, the way the chain rule works, is notice how the numerator of this fraction and the denominator of this fraction are exactly the same. So in some sense they cancel each other out, and it brings you right back to ddx. So all we're doing is, if we find the derivative with respect to y of y, we have to multiply by dy dx, so that in some sense we're still taking the derivative with respect to x. Because notice how dy cancels, bringing you right back to ddx. But this we can find the derivative of. d dy of y. So we're going to simplify that by the next line. And once again, this is line 4 now. So we're doing something similar later down the line for this problem. But we have d dx of 3x. That's simply 3. The derivative of 3x is 3. So 3 times y cubed. And now we're adding 3x. And now we're taking the derivative with respect to x of y cubed. But for this, we can't take the derivative with respect to x of some variable y. So we're going to go d dy of y cubed. This we can simplify. But now we need to multiply by dy dx. Because remember, we're finding d dx. So in order to bring this back to d dx, we need to multiply by dy dx, so those dy's cancel, bringing you back to d dx. So now we write our minus 1 equals 0. So now for the next line of this problem, we have 2xy plus x squared, and now d dy of y is simply 1. The derivative of y is just 1. The same way the derivative of x was 1 in a previous part of the problem right here. d dx of x gave us that minus 1. So d dy of y is going to give us 1. So we have x squared times 1 times dy dx. And now we're adding 3y cubed. And we're adding 3x. And now the derivative with respect to y of y cubed is 3y squared. So we're multiplying by 3y squared times dy dx. Minus 1 equals 0. So now the strategy for the rest of the problem, what we need to do is we need to isolate the dy dx terms because we're solving for dy dx. So before we move to the next line, let's just note, for these problems, the strategy is to isolate any term with a dy dx. So we have the x squared dy dx, and we have the 3x 3y squared dy dx. So those two we want to group together. So now for the next line, we will get rid of this now since we don't need the chain rule anymore. So for the next stage of this problem, what we want to do is group all the dy dx terms together. So for line 6, well, we're just going to rewrite what we have. We have 2xy plus x squared dy dx plus 3y cubed. And now we have plus, now 3x times 3y squared we could write as 9xy squared. And now times dy dx. And now we have minus 1 equals 0. So what we need to do, as I said before, is the dy dx terms, we need to keep those on one side and get everything else on the other side. So our next step is to subtract 2xy from both sides. Then we could subtract 3y to the third from both sides. And we could add 1 to both sides. And now I'm writing plus 1 first because I like to lead with positive terms with these type of problems. It's usually good etiquette to start with a positive term. So now 2xy minus 2xy cancels. 3y to the third minus 3y to the third cancels. Minus 1 plus 1 cancels. So now on the left-hand side, all we have is x squared. Now this is line 7. We have x squared times dy dx plus 9xy squared dy dx is equal to, and now we have 1 minus 2xy minus 3y cubed. So now we need to separate dy dx from both of these. We could factor dy dx out. So in the next line, we have dy dx. We're pulling a dy dx out of each of those from the left-hand side. And now what's left on the first piece, we have x squared. And on the second piece, we have plus 9x y squared. And this is still all equal to 1 minus 2xy minus 3y cubed. So now the last step to solve for dy dx, we're going to divide by x squared plus 9xy squared on both sides. Plus 9xy squared. And now on the left-hand side, x squared plus 9xy squared will cancel. So we have the final line of this problem. We have dy dx is equal to 1 minus 2xy minus 3y cubed divided by x squared plus 9xy squared. So this is our final answer to this problem. So this is how we use implicit differentiation, but it's really important to see that the chain rule is such a big part of this. Some teachers would show, like let's say we're finding dd, the derivative with respect to x of y squared. They say, oh, go 2y and then throw a y prime on. The reason why I'm not a big fan of this technique is because it hides the chain rule, and later on you're really going to need the chain rule to solve something like related rates or change of variables when you're doing polar coordinates or parametric equations. So learn how to use the chain rule. It makes these problems a lot more clear. Okay, well this is going to conclude this video on implicit differentiation. Thank you all for watching, and I hope that this was helpful.